So we are now on the lecture you've all been waiting for, the root locus definition lecture. So today we'll do 5.1, part of 5.2, probably finish up 5.2, and hopefully get the rest of 5.3 on Friday. So that's the plan. In this lecture we'll define the root locus. 5.2 we're going to sketch the root locus, and then in 5.3 we're going to learn how to use MATLAB to do some root locus stuff. So that was our rough sketch of our week. The start of this is, remember what we tried to motivate at the beginning of lecture on Monday was that we want to find the locations of the closed loop poles, right? So after we close the loop, we want to know where those poles are going to be, because where they are dominates the behavior of the system, the stability of the system, the steady state response of the system, and then also the transient response of the system. So those closed loop poles, finding where they are is important, but we want to do that with our controller gain at least unspecified in the system. We want to know where those closed loop poles would be for all possible values of the controller gain, okay? And that's what the root locus is going to give us, is a description of that. So, a feedback system's closed loop poles determine its stability and transient response. These poles depend on parameters in the controller, often the gain k as shown in figure 5.1. So we're just going to do the simplest controller possible, which is actually like not, it's like, although it's super simple, it's surprisingly effective in some cases. So here's our situation. We have a plant that we want to control, right? Plant. And we are going to control it by putting in some input u to it, and it gives some output y. What that input u is what we're trying to decide from this control loop. That's why we're doing this control loop thing. If we knew what to put into the plant to make it behave how we want, to give us the output that we want, without doing all this feedback in the controller thing, if we just were omniscient, we wouldn't need all of this other stuff. But since we're not omniscient, we need to measure what the actual output is and feed it back. And notice I put a transfer function in the feedback loop for this description. That transfer function might be 1, so we might have unity feedback, but I'm going to leave it a little bit more general in this derivation. Or really, it's more of a description. And then we feed it back. We compare it to what we want this output to be. Okay, so, and clearly it's going to be, we want this output to be once it goes through H, right? Because it gets to go through H, compared to what we would expect it to be once it goes through H. Maybe H is just a photodiode that maybe we want the light intensity to be something, and a photodiode is going to convert that to a voltage, the light intensity to a voltage for us. Maybe that's what H is that conversion. Maybe it's just described by a constant, like 74 millivolts per lumen, and I don't remember what the abbreviation for lumen is. But anyways, maybe that's what it is. It could be anything. It could be a transfer function with s's in it. It could be more complicated than that. So typically it describes our measurement process, and then we compare it to what we want that output to be, right? We subtract it. If there is a difference, we're going to have an error left over. That's what we call this E. What comes out of that summing function, the error. And our simplest controller, so this is going to be our controller. The simplest possible controller is to just put in a gain in there. So like multiply whatever that error is by some constant, and then directly put that right into our plant. So we're going to start out with that as our controller and see what we can see, okay? And it turns out that using this and then iteratively adding complexity to the controller and finding the gain is a pretty effective way to sort of bootstrap our way to a design. And that's exactly what we'll do. So this is, remember the closed loop transfer function takes us from this command to this output. So you put in R, you get out Y. So this is the closed loop transfer function, right? So we could just rewrite this whole block, this whole diagram as a single block, right? Find the closed loop transfer function. And we did that derivation in chapter 1 of these notes, right? So a few weeks ago, before we did all the transient response stuff, before we did the steady state response stuff, before we did stability, we talked about how to find the closed loop transfer function. And here is that closed loop transfer function, just like we derived it before. You can go back to that derivation. I think it's like lecture 1, 2, or 1, 3 or something like that. Notice that our k shows up, boop, right there in the denominator of the transfer function. So it's going to affect the poles of that closed loop transfer function, right? I don't know why it shows up like boop, but it does. This is a good thing, right? Because we want, if we change this gain, our controller gain, we want to affect the location of those closed loop poles. That's kind of the whole point of having the controller in there, is so that we can affect that, right? We want to change how that system is behaving. So that's good. But the bad news is that we don't know how to solve, if this is higher than like second or third order analytically, we don't know how to solve for what the roots, the poles are going to be with some arbitrary value of k. We have to choose some value of k, right? Okay, so I'll expand on that point now. So 3 definitions of transfer function types inside of this block diagram description. So we define the forward transfer function to be the transfer function from the loop's error to its output C. So whatever the transfer is from, I don't know why I wrote C. Output Y. This should be Y. So we want to know the transfer function from the error to Y. We call this, just define it to be the forward transfer function. What is it in this block diagram? What is the transfer function from E to Y? You got to combine these 2 blocks, right? There are 2 blocks. If there's only one block, the transfer function would be whatever's in that block. So if there was no k here, we would just have g as our transfer function, our forward loop transfer function. But so we've got this controller with a gain k in there, we have to, when they combine, when they're in a sequence like this, 2 blocks, this is multiplicative, right? So we could just combine this by saying this is just kg. Who used to be a good basketball player, but I don't know, probably retired now? I haven't watched the NBA in a long time. Okay. So this is the forward loop, the forward transfer function is whatever's in the forward path, so kg. So it's a pretty simple definition. We're going to use that term, forward transfer function, from time to time, so it's good to know it. The next bit of definition here is feedback transfer function, which is defined to be the transfer function from the output, so y, to the feedback summation. So from the output, y, to the feedback summation, so this is going to be h, right? The feedback transfer function is h. So the feedback transfer function is whatever's in the feedback loop. And finally, the open loop transfer function, which a lot of people get confused with the forward transfer function, but it's very important not to get that confused. The open loop transfer function is defined to be the product of the 2. In our case, it's simply kgh. So it's the product of the forward transfer function and then the feedback transfer function. So it's kg, in this case, the forward transfer function, and then times h, which is the feedback transfer function. So kgh. It's the open loop transfer function. Okay, so kgh, that's in our case, this open loop transfer function. It's an important definition. We use this term quite a bit, the open loop transfer function. And there's a lot of confusion on that term, so I thought I would be very specific on the definition. We break down g and h into numerators and denominators. So we're going to look a little bit deeper into what this looks like for our example. So g is g numerator divided by g denominator, and h is h numerator divided by h denominator. Now we can see how these affect the closed loop transfer function. So I took that closed loop transfer function equation and just plugged in g and h from equation 5.1. Okay, so I have all of the numerator and denominator aspects of g and h. And I simplified it a little bit. And you end up with k times the g numerator shows up here, and h denominator shows up in the numerator of the closed loop transfer function. And these, the denominator of the closed loop transfer function has k in it, has the denominators of g and h affecting it, and the numerators of g and h affecting it. So dang, it's got like everything affecting it. But there are some really interesting things that happen if you look closely at this expression. So the closed loop poles, so remember closed loop poles are what happens when you set this all equal to 0, right? So if the closed loop poles depend on k, so that's the first observation. But for controller design, k is that for which we are solving, right? So we want those poles to be in a certain location. So we want to solve for the k that would make that happen. We want them to be in some desirable location because we're doing design now, right? We're not doing analysis. K isn't given. We're having to come up with k. So sort of a different process than just like, oh, here's a controller. What are the poles? But now we need to be able to say, okay, here are poles that we would like there to be, or maybe not specifically. We would just say, I would like the rise time to be like this. What should my gain be? That's the problem we're trying to solve. We have some performance characteristic we would like, and in chapters 2, 3, and 4, we talked about the 3 types of performance characteristics, right? Stability, the transient response, and the steady state response, steady state error. So we might have some performance criteria described like that, right? Like certain percent overshoot, certain steady state error, maybe less than a certain amount, and it has to be stable, okay, in closed loop. So that might be our requirement. How do we find the gain, k, to make that happen? Or a gain that solves this problem? Often the times there are lots of gains that would work for our criteria. Okay, so 2 caveats here. So an analytic solution for the closed loop poles is intractable for systems of order greater than 3. So, I mean, realistically, even if it's higher than second order, we don't really even think about doing it in terms of analytic solution. Even for second order systems, we typically don't, just because it's so common to have higher order systems. We just usually treat them all as like, we're not going to solve closed loop for what the gains are going to be. And for a given value of k, a numerical root finder is very effective. So like it's great if you have a value of k that you want to try out, you can find out where those closed loop poles are going to be. But without checking all of them, you don't know the total solutions, right? And there are an infinite number of k's you could choose. So how do you go about doing that? So that's what this root locus technique is going to give us, is we don't have to solve them in closed loop form analytically, but we can still design for what gain we want. So we'll expand on that in the coming lecture. But the second point I want to make about this expression is that as k goes to 0, this term goes to 0, right? That becomes 0. So we're left with the denominators of g and h in the denominator of our closed loop transfer function. And that's really interesting, right? Because the denominators of G and H give you the poles of G and H in there. And that's our open loop transfer function poles. So the closed loop poles approach the open loop poles as k goes to 0. So if you have the gain set to 0, meaning doesn't matter what error comes in, you're going to put 0 in for your input to G, then the closed loop poles, if you close this loop, essentially it operates open loop. It doesn't, your closed loop poles are just however your open loop poles would have been. It's like nulling out the effect of your controller. Okay, that's an interesting little bit, right? So we don't know what it is for all k, but for k equals 0, it's just the open loop poles that we've got. And that is very similar to the next point, which is as k goes to infinity, the closed loop poles approach open loop zeros. So as k becomes infinite, you can, if you can sort of see from this expression here, the effect of the open loop zeros, which are G and H numerators, right? The numerators of our open loop transfer function, set to 0 give us our open loop zeros. That's what this expression, the poles for this expression approach. So as k goes to infinity, the closed loop poles approach open loop zeros. In other words, if you were to summarize this, these last 2 points, it gives us a start and a finish for our closed loop pole locations when k is varied from 0 to infinity. We want to know where those closed loop pole locations are for all k, right? For k 0 and k infinity, we know that it's the open loop poles, and then for k goes to infinity, it's open loop zeros. So we know the endpoints of what we want just from looking at this expression. And this varying of gain from 0 to infinity and finding the closed loop poles is a procedure we'll now define as the root locus. That's exactly what the root locus is this varying of the gain from 0 to infinity and figuring out what the path is that the closed loop poles trace out as you vary that gain. So it's sort of like we'll find all the solutions for gain k. It's not a process that they jump around, right? If you change the gain by some small amount in the vast majority of systems, you're just going to vary continuously in the complex plane where those locations of the poles are. They're not going to go from like one side of the plane to like, you increase the gain by 1%. It's not going to like suddenly make those closed loop poles go way over to the other side of the plane. They're going to vary continuously. So we're going to like trace out where those would be. And you might have already guessed that if you're looking for a lot of solutions to something, like, okay, we don't want to find every solution analytically, of course, for every gain, right? That's just crazy. But a computer tool would be able to find a lot of them and show us a plot of what those look like. And that's one of the reasons why MATLAB is going to be very, very helpful for this. So we'll get there. Okay. Now we're ready for the definition. Okay. Here we go. The root locus is the collection of closed loop pole locations for varying proportional controller gain k. That's the definition of the root locus. So it's really like, it's not super mysterious. Those closed loop poles are exactly what we're interested to know, right? And so the root locus says, okay, you want to know where those closed loop poles are for all the different k's? We'll just give you a graph of the whole thing. We'll give you all the solutions. It's the collection of all those closed loop pole locations, all those closed loop pole solutions for all the different gains. Recall that for a feedback system with plant G and feedback transfer function H, the closed loop transfer function is this. So this is 5.3, and that finding the poles is difficult in general, right? This is just from the last section. However, let us consider our observations from this previous section. We know our starting points. At k equals 0, the closed loop poles are equal to the open loop poles. And we know our endpoints. So as k goes to infinity, the closed loop poles are equal to the open loop zeros. Therefore, we can consider the root locus to be a collection of curves that begin at the open loop poles and terminate at the open loop zeros. Great. So now it's just like, cool definition, bro, but like, how do you do that? And that's what we're going to talk about now. I know that's how you guys think in your heads. Cool definition, bro. All right. So the magnitude and phase criteria. The closed loop poles can be found by setting the denominator of the closed loop transfer function to 0 and solving for the values of s that satisfy this condition. Every pole for any transfer function can be found that way, right? Examining the closed loop transfer function, which is 5.3, rewritten in 5.3 so that we can look at it easily, we see that this is equivalent to, so if we set 1 plus kgh, set that equal to 0, we're going to find those closed loop poles, right? If we could solve for all of the values of s, we would find them. So we say 1 plus kg, I'm going to drop the of s's because I think it makes it harder to look at when you're writing it, equals 0. So kgh, 1 plus kgh equals 0. We could rearrange that. So I'll say it implies that kgh is equal to what? I know you guys can do this one. This one's 7, exactly. -1, right? So it's equal to -1. We know that if we find the solution for kgh equals -1, we have found the values of s that are closed loop poles. Okay. So that's true, but it's like, okay, but how have you helped me? Great, bro. So if we were to rewrite -1, I don't know. I don't really know. -1 in terms of a polar representation, it would be 1, right? So it has radius of 1, and in the complex plane, right, it could have an angle which is, well, it's going to be pi, right? But it's also going to be multiples of pi. So 1 plus 2m pi for m being an integer. So I'm saying that kgh has to have magnitude 1 and phase pi, or 3 pi, or 5 pi, right? Or etc. So that's the equation that's going to give us these two criteria, the magnitude and phase criteria. Okay? So the magnitude criterion, it's just the one, is that, and I'll write it out in a sentence. So the root locus must everywhere satisfy the criterion that the magnitude of this left-hand side, which is kgh, right, must be equal to the magnitude of the right-hand side, which is what? 1, period. So the magnitude of kgh, magnitude of the open loop transfer function, that's what kgh is, must always be equal to 1 if you're going to have a solution to the closed loop transfer function poles, right? So there's the magnitude criterion. The phase criterion, you might have guessed, we did the magnitudes, now we're going to do the phases. They have to be equal to. Okay? So the phase criterion, so we're going to say the root locus must everywhere, musty everywhere, satisfy another criterion. That the angle of KGH should be equal to it's just going to be that, right? 1 plus 2m pi for m an integer. So it's got to be equal to pi or plus or minus any integer multiple of 2 pi. So it's got to have an angle of equivalent to 180 degrees, right? So that's the phase criterion. So it might just look like we have just shuffled around the deck chairs on the Titanic, and we still don't know how to solve for this stuff. And it's actually true. In closed form, it doesn't really help us with a closed form solution, but it's going to help us sketch the root locus. Okay. You can use MATLAB to give you all of the points, just solve for all the values for different Ks. We're going to do that shortly, but we're going to first learn to sketch it, and getting a little ahead of ourselves, but yeah. So I'll just stop there. We're going to learn to sketch it from these two criteria. So these criteria are always satisfied, and they will be our guide to understanding, sketching, and designing with the root locus. And I should be careful here. It's not just sketching, like I say, also getting a feel for and using the root locus for design. These two criteria really help give us that insight. But it's not yet, looking at the equation might not yet illuminate things for you, but I think that it will. What about negative gains and positive feedback? So we did this derivation for a really specific feedback loop, right? We had negative feedback. We had positive gain k from 0 to infinity, we were assuming, for a lot of this. Actually, in these two formulas, we didn't assume that, but you could assume that. So, typically consider only non-negative gains for the root locus, since negative gains typically lead to instability, okay? However, this is only true for systems with positive open loop transfer functions, which is the vast majority of them. You're going to have a positive open loop transfer function. You're not going to have a negative sign out front of the whole thing. When encountering a negative open loop transfer function, which does happen occasionally, it is advisable to temporarily treat it as positive. So just like flip the sign, proceed with the controller design, then multiply the controller that you come up with at the end by -1. Okay? So dealing with a negative transfer function, this would be the recommended way to deal with it. If one suspects a negative gain might be of service in a specific controller, so a little sidebar, often slightly negative gains can remain stable. So the system in closed loop, if you have a slightly negative gain, oftentimes it'll remain stable for a little bit and then it'll go unstable. Or if one is building an unstable system intentionally, develop the root locus for negative gains or equivalently positive feedback. So if that's what you've got in your control loop, positive feedback, which you typically wouldn't do, but if you're trying to intentionally make a system unstable, and there are some examples of when you would want to do that. For these occasions, there's this is just the Nice textbook. There's a section in the Nice textbook that talks about how to do negative gain root locus construction. Sketches. I don't think it's useful to learn the sketching rules necessarily, because you can always fall back to MATLAB, and if you need to do a negative gain one, you can have MATLAB give you the negative gain root locus. Totally fine. It'll just spit it right out for you. You don't need to relearn how to sketch the root locus for the negative gain or positive feedback situation. I just don't think it's that useful. So if you're interested, though, you can see Nice. he's got lots to say about it. Okay.